So, welcome back after the break. I am now going to discuss the terminology of the constituent of machine learning algorithms and models, starting from the basics, so basic constituents, so the features and the descriptors. So what I will be describing is not universally accepted, but it's becoming more and more assessed at least in material science. I will drive mainly by this paper from the group of James Kermode, who is in the Nomad Center of Excellence, and also from papers from us and from Gabor Sani group that is also part of the Nomad Center of Excellence. So I would like to start introducing what are features, and to do that I introduce this kind of Christmas tree that I will populate slowly, and the idea is that we are going to fit some property as a function of some constituent, and this constituent build a whole hierarchy that I will justify step by step. So at the bottom are the primary features. So we are talking about material science, and specifically to material science we typically start from the positions of atoms in some unit cell and physical chemical properties of the chemical elements themselves. So of course basically they are identified by the atomic number, but it's also typical that one introduces features of the isolated atoms like the electronegativity or similar. These primary features, as they are, need to be combined in some way. For example, if a feature is related to a full unit cell, it has to be somewhat averaged, or they have to be transformed in some way in order to satisfy some invariances. I will come to invariances in a second. So the combination of these primary features will make the features that enter the model. So some kind of representation of this input information from each material. Now the features in turns would be the constituent of a vector that is called the descriptor. Now see the difference between the parentheses and the square brackets. The descriptor is just the collection of all these features that are created by manipulating in some mathematical way the primary features. In turns, this descriptor it builds the so-called representation. So typically this step is done inside the machine learning algorithm, so is beyond the intervention of the user. But not all algorithms explicitly build a representation out of the input descriptor. Some of them utilizes directly the descriptor in order to build the next step, that is the model. So at most this representation will be a kind of identity step. But in several cases, like in deep learning, the crucial advantage of deep learning is that it builds some internal representation that makes the best use of the descriptors used as an input. And this builds a model, and you have also the possibility that several models contribute to describe the property. It is the case of the so-called ensemble of models. You will see an example in Daniel Speckard lecture in the near future. So this is the whole construction, and I want to dig a little bit more on what do we ask to this descriptor in order to be a legitimate one, at least in the context of material science. Before that, I repeat this diagram in order to repeat again that there are algorithms that build this representation as part of the algorithm. These are deep learning, and another one is symbolic regression that actually I will introduce next week. So what do we ask to a descriptor? So this is really a list of wishes that we ask to the descriptor. And the first one, there is no particular order of importance. All of them have to be fulfilled. But let's start from something simple to grasp. It's invariance. So this descriptor has to be invariant under at least symmetry operations that are permutation of same atom in the representation and translation and rotation of structure. So all the equivalent atoms in the structure and translation and rotation, of course. Another property is the sensitivity. So small changes in the atomic position should result in proportional changes in the descriptor and vice versa. So this is quite important in order to allow the learning algorithm to react smoothly to the change in the descriptor. If the descriptor changes abruptly already by little changes of, say, coordinate or materials composition, it will be hard for the descriptor, for the model to follow to describe what is going on. On the other hand, of course, if properties change fast with some small changes of the descriptor, one should not be too rigid about this constraint. So in this, there could be some abrupt changes that need to be captured. Related to this is the differentiability, so that there is a continuous function that is also differentiable in mapping the descriptors. And also here one has to be careful. There could be discontinuities and also lack of derivatives in some situations. So not always fulfilled. Another wish that is certainly interesting, important, but not always strict one, is the global uniqueness. So the mapping of the descriptor should be unique for a given input atomic environment. So the mapping is injective. This is true. It is great if there is a one-to-one correspondence between the structure and the descriptor, but it should be not thought as something that could never be broken. And I will come back to this when I introduce a little bit more terminology and concept about regression. The dimensionality is somewhat related to the uniqueness. The dimension of the span hyperdimensional space of the descriptor should be sufficient to ensure uniqueness, but not larger. So again, as much as needed, but more would give too many degrees of freedom that are uncontrolled, and the machine learning algorithm would be in trouble to cope with. Scalability, the descriptor should be easily generalized to any system or structure with a preference to have no limitation on number of elements, atoms, or properties. So it's important that whatever is changing in the system across our data set and the representation of the descriptor doesn't need to change, otherwise the machine learning doesn't know exactly what to do. The complexity, this is the computational complexity, this is vital. So the descriptor should have a low computational cost, so the method can be fast enough to scale to the required size of the simulation and to be used in high throughput screening of big data. Of course, if building the descriptor is computationally very intensive, even to compete with the methods that are used to produce the reference data, then there is no gain, clearly, for the machine learning utilization. The last point is the interpretability. So features of the encoding can be mapped directly to structure or material properties for easy interpretation of results. So one sees what is in the descriptor. I will now go fast on this because I will come back to interpretability in the next part of the discussion. So I want now to introduce present a couple of descriptors that have been used in material science that I find particularly imaginative in order to realize that the descriptor can be not strictly a function of the coordinates or specific properties of the material, but something a bit more creative. So this is the case of the descriptor introduced in the group of Rampi Ramprasad, who will be a lecturer later in the course. They had this system that is basically a collection of polymers built up by these 7 blocks. And the descriptor that came up is a kind of way of encoding this kind of DNA chain of the polymer. So you have which block is appearing in the sequence, and what they had is number of times a certain block of these 7 appears, number of times consecutive pairs of the same block appears, of the triplet of the same block appears, and this makes a 20-dimensional representation of the system. Quite creative, I would say, that yielded a good predictive model. Another example is from the group of Stefano Curtarolo, another key player in the field, and what they did was to use the electronic band structure and the electronic density of state as fingerprint in this way. So the bitmap, the figure was coarse-grained in some way by representing what happens in this figure by means of histogram, and this was mapped into again some kind of DNA string for both the band structure and the density of state. So what is presented to the model is these strings that takes into account where these lines are in the figure. Okay, let me now go to supervised learning, and in the following I will be addressing quickly the other 2 aspects, but clearly supervised learning is kind of the most utilized in the field, and requires a little bit of a careful introduction. The problem of supervised learning is estimating a function that goes from some input features x into our target variable y, and this is mathematized in this way as y is a function of this x plus something else. So x is our descriptor with so it's a collection of features, and the something else is an error term that does not depend on x. So note the simplicity of this formula that is already containing something very profound. So there is a term that does not depend on the descriptor, and this part of what makes our target property. So by construction, this term is not seen by the descriptor. So whatever one does, the descriptor does not capture this term here. So to fix the ideas, a possibility is a multilinear model, so just a linear combination of the features in order to yield the property. It will come back later, the linear model. Once we have established the kind of model that we are after, we look for a specific good function that would approximate our observation y hat, and this is our statistical guess for the function f. So it is interesting at this point to look into the error that one makes when evaluating the value of y by means of this function f with respect to the true values. So this term here is the expectation value of the square difference between these two quantities over all the observations. Now here we are talking about the data that are not used to build the representation of f, so the so-called training data. Here you're using so-called test data to evaluate this performance of the model, and some simple math would transform this expectation value into the sum of 2 terms that are both positive. One is this so-called reducible error that is essentially the difference between the predictive, the true function and the one fit from the data. And then there is some irreducible error that comes from what is not captured by X. So now it is very important to realize that this epsilon, and therefore the induced error, so-called irreducible error, is present even if we have fully deterministic data. So you don't need any stochasticity in the data. Why? It is just introduced by something that is not seen by the descriptor. Now, this is related to the uniqueness point that I was talking about before. So if something is not seen by the descriptor, we are certainly introducing some error due to the fact that there is something not accounted for from the descriptor. The other thing that we may be interested is look into the model, so this f function, and ask questions. So this in the field is called inference, or also interpretation. So the questions could be which features are associated with the target, so which of these xi are actually actively in the model, what is the relationship between the target and the feature, can the relationship between the target and each feature be adequately summarized using a linear equation, or is the relationship more complicated? Because I mean, we should not forget that linear relationships are particularly simple and can yield quite some insight. So whenever there is the possibility of grasp a linear relationship, it should be immediately captured. Now I'm going a little bit into assessing the performance of the model. So we have always in mind how the model performs with the data that were not used for training it. And let's first look at this plot here, in which we have given data empty kind of circles that are the training data, and we are evaluating the performance on the full circles that are the test data, let's say. And we have the three kind of models, some simple linear, some more complex with the black line, and some even more complex with this wiggly blue line. So this is related to the flexibility of the model, so essentially how many parameters we are going to fit in order to build our model. And the purpose of this figure is to introduce some terminology. So if we look at the error that we make when we analyze the model, we have a so-called training error. So basically how good the training data are reproduced by the model. Clearly, the more the flexibility, the more this training error goes down. The other is the test error. So basically the error that we are doing on the data that they're not used on the fitting, and this tends to go down when the flexibility increases for a bit, and then goes up. This branch of the curve is typically called overfitting, and means that the curve, the fitted curve, follows too much the input data and is not able to generalize. So I'm just introducing the terms that you will hear over and over in this course, and if you are going to do a lot of machine learning in the rest of, so in the near future. And the other branch is called underfitting symmetrically, because the model is not enough complex to capture what is going on, so the error is also high, and ideally we want to be in the sweet spot where we minimize this error. Okay, in order to further analyze what is happening, it is instructive to think at the so-called bias-variance trade-off. This is a further analysis of how this error is built. So again, it is the squared error of the predicted values of some input x with respect to the true value, and this is averaged over all the input, and in this case, over all the data points. So this is a bit involved to derive, but what happens, we have the sum of three positive terms, so these are the variance of f hat. This changes every time you change the training set for doing the analysis. And then you have a term that is called bias that is actually inherent to the model. So if you have a linear model or a higher level model, that there is an intrinsic term that is called bias. So it is independent of the training set that it used for training. And then we have our old friend, it is irreducible error. So if we analyze what happens, we have that the bias by construction goes down with the flexibility, cannot do more less than that, different from that. So when there is more flexibility, this term goes down because there are more possibility for the model to adapt to the data. On the other hand, this variance goes up by construction, because essentially the more freedom the model has, the more it will change every time the training set changes. And the sum of this plus the irreducible error gives our mean squared error. So this is the same the decomposition for the same kind of scenario that I showed in the previous slide. A simpler scenario is a kind of linear fit where there is a certain amount of this irreducible noise, but essentially the linear fit is capturing most of what is going on. Therefore, there is almost no change in the bias term, and the variance keeps on increasing. So the sweet spot, the minimum, is actually at very small flexibility. The higher flexibility is wasted in following the wiggles that are not important. So I want to make a little kind of intermezzo on linear fit in order to convince you that you should not really disregard linear fits. And the example is coming from astrophysics. So most of you know that the astronomer Hubble at some point had data on the recession velocity of galaxies and their distances. So pioneering was the way these values were measured. And then he proposed a model in order to link the two quantities, and that was just simply linear. So the recession velocity is linearly correlated to the distance. And that means that one makes a linear fit through the data. And you may say, well, okay, yes, there is certainly a trend, but now linear seems a little bit far-fetched. I mean, the point is that behind this idea, or beyond this idea, Hubble could build a model of the universe that actually is still, to some extent, valid today. And if we look at the modern version of the Hubble diagram, essentially we are still doing a linear fit in order to fit the Hubble constant. We completely understand why there is this scatter with the so-called Virgo cluster. I am not going to go into the details here. The point is that we have a model of the universe in which this simple relationship is still valid to some extent, at least as the first approximation. Now, what you for sure you have noticed immediately is that the modern value of the Hubble constant is quite different from the value that Hubble had found, and the main reason is that he had data only until 2 megaparsec. Now we have data until 20 megaparsec, so it was fitting only in the initial part of the curve, and it happened to be much steeper than it actually is. End of the digression on linear models that you should not disregard when just because they are too simple. And then we can go on to actually situations in which actually the model has to be more complex. And so this is the situation depicted in the figure here. These are the data, and certainly you need something more complex than just the linear fit, and you see it in the terms variance. So the bias again and the variance, and then you need a higher complexity. So now these are kind of a toy model. So we know exactly what is the generating function of this data. So we know essentially what is this epsilon term. Of course, in real life we don't really know. what it is. So this is a conceptual analysis, not so useful in practical cases. Let me go further to talk a little bit about different metrics. First of all, we have the metrics for the learning, and we have seen in regression the kind of natural metrics is the mean square error. But if we go, for example, to classification, we need a completely different metric because, of course, the mean square error doesn't have any significance for a classification problem. And to fix the idea, let's say we are classifying materials if they are metals or non-metals, and then kind of natural, as much as natural is the mean square error for the regression, the natural metric for classification is counting essentially what is misclassified. So this indicator function is one if the argument is true. So we count how many times we have a disagreement between the prediction and the truth that is known for the training, and this is our misclassification error. Okay. I now want to introduce one of the main characters of regression in the context of machine learning. I mentioned this already when presenting the diagram of machine learning inside artificial intelligence, and I said that learning is essentially determined by the regularization, because we need that the model is improving when we have more data points to deal with. So now let me start again from the linear model, and we have this minimization where this is the property projected over the data points or materials, and this is the matrix of the descriptor, and these are the unknown coefficients that are learned by minimizing this expression here, that is again the mean square error. So now the thing to be noticed is that it's typical that one has many more variables, so the columns of this matrix, than the number of observations. So it's the typical situation in machine learning for several reasons. And therefore, one has a situation in which this system, this expression is not fully determined, and one needs to add some more information. First of all, let me say that this 2 here is the signature of the L2 norm, and here is just the Euclidean norm, so the so-called P norms are defined in this way. So if you have an entry here, so here would be P minus DC, it would be the sum of the single entries to the power P. The sum is then one takes the P root of this sum. These are called P norms. Now you see the 2 norm that is very known to everybody, the Euclidean norm, that there are other used norms, P norms in the field, and you will see extensively them in the next lecture by me, and also in the Santiago Rigamonti's lecture. So what I needed here is to introduce now a term in which when we have the situation, the typical situation that there are more columns in this matrix than rows, so the number of observation data points, we have to put a condition on the solution in order to disambiguate the possible many valid solution. And the condition here is to impose that the norm of this vector itself is as small as possible. And this is done by making this combination of the error that should be small, and also these other terms that should be small. And there is a weighting parameter that weights the relative importance of these 2 terms. Now keep in mind this lambda, and I am introducing first another ingredients in order to reveal why I have now introduced this complication, let's say. So by what I have to say is that this term here is the so-called regularization. So So this is, in general, a term that tries to reduce the complexity of the model against the tendency to have a more complex model to have a better fit, because more complex is the model, the more you can properly fit your data. So now let's imagine that I express my linear fit as a sum over Gaussian function. At the moment it's not important why I do that. There are good reasons to do that, but let's just fix our mind to the fact that I have that my property is expressed as a sum over Gaussian function. I can always do that, and this is let's say the descriptor for a specific data point, and this is the descriptor for the material, the data points for which we want to evaluate the property, and what we have are these linear coefficients Ci, one for each data point. And what we have to do is to minimize this expression. So now we recognize this is the error, and this is the regularization term. A little bit more complex than in the slide before, but keep with me. So what you have is this lambda parameter and something that depends on the Ci and Cj for the different data points. Now you should focus your attention on this lambda and sigma, that are two parameters that cannot be fit in the same way as the other, the Ci are fits. These are linear terms and can be learned by just solving the linear problem, that is this linear superposition of basis functions. So for this we need a new device that is called cross-validation, that you for sure have heard already, and also here there is a little bit of, I would say, confusion on what cross-validation actually is. Cross-validation is a device that allows us to determine parameters that are not linear, or in general are not the parameters that our learning algorithm is designed to fit. I'm being vague. In neural networks, things are not linear at all, but there are some parameters that are fitted by the neural network algorithm itself, and there are other parameters that cannot be fit in the same lot. So these are all called, in general, hyperparameters. And as you see here, there are of two kinds. One here is some nonlinear part of our basis function that needs a kind of independent assessment. Is the width of the Gaussian. What should this width be? We don't know, not necessarily. And the other one is this lambda parameter. That is the kind of more to the model itself than the way we express the basis functions. So in both cases, what we can do is to train the model for different values of lambda and sigma, and find for which value of lambda sigma we have the smallest error. Which smallest error now? Errors on data that were not used to train the coefficient Ci's, otherwise it would be pointless. We use other data. So what people do in practice is to start with some fixed value of these hyperparameters, train the model on some part of the data that is called the training set. What is left out of the training set is called validation set, and one assesses the performance of the trained model on this left out data. Why doing that? Well, first of all, you repeat these things over and over over different split of training versus validation, and then average over these splits in order to have enough statistics. And then you say, okay, now I change lambda and sigma, and there will probably be a combination of lambda and sigma for which I have the smallest error on the test data, and here is where I like to have my model sitting. So all this procedure is called model selection. That is different from the training of the model, because this is intrinsic to the kind of algorithm that one is using. So this cross-validation is general. You can use for every kind of machine learning model once you have identified what are the hyperparameters that you want to fit. Now, I will just mention very briefly that the cross-validation is not the only way to assess the hyperparameters. There is a whole set of machine learning algorithms that are under the umbrella of Bayesian inference that will not be treated in this course actually. They are a bit specialized, and there are other ways to assess this lambda and sigma. But this is certainly a possible way that you will be seeing invoked many times in this course. Okay, now I want to kind of discuss a little bit the idea that when we analyze our results, so by analyzing the result, it means now we are looking at the test data. We may want to have much more information than just looking at the mean square error. That is what we use for training. And other candidates would be, for example, the mean absolute error. That is actually the error that we expect to commit on average on new data rather than the square root of the mean square error. That is a bit convoluted. It's just typically very good mathematically for training the model. Another situation could be the median. Another good metric is the median, that is the point in the data such that 50% of the error are below that level, and 50% of the error are above that level. So it's another kind of center measure. Or other percentiles, so like the 25th percentile or first quartile is the level at which 1/4 of the errors are smaller than this, and the remaining 75% is above this level. And people have found ways to represent all this information in a kind of summary plots or diagrams that are called box and violin plots that I will briefly introduce now. So this is the results of some machine learning analysis that we did in my group, and you don't need to know anything here, just that there is some learning done by changing some hyperparameters. And each of these square points refer to the root mean square error of some settings, and then we change the settings. But fix your attention on only one of these squares and what is around this square. So this is a summary of the distribution of errors in some sense. So you have the root mean square error, this field square. You have the mean average, absolute error that is marked by the cross, and then we have the real, so the actual box plot. So this rectangle here, where you have the median in the middle, and the two extrema of the rectangle are the 75th and 25th percentiles. And traditionally the whiskers, so these things protruding here, mark, for example, the 5th and 95th percentile. So where most of the error is in this interval here. So this is much more information than just saying that the root mean square error is this point and the mean absolute error is this other point. So you keep track of the distribution of the data, of the errors. And as a similarly instructive representation is so-called violin plot, in which now you represent the whole distribution of errors. So it means that most of the error here are at this level, and then they become fewer and fewer. Here the two colors are because one is training and one is test error. Not very important here for this other paper we published. It's just to show how these things may work and may be important. A similar interesting analysis, but with completely different metrics, can be done on classification. So just saying what is your misclassification error does not give much insight on a classification kind of exercise of learning. And so for doing that, people use the so-called confusion matrix, a name that probably you have already heard, and I'm going to introduce it very briefly. So to fix the idea, let's say our classification is the material a metal. So positive here means being a metal, and negative not being a metal. And so the matrix has on this side here the ground truth, and on the other side the prediction, and one counts how many times the prediction was positive and the label was really being a metal. negative versus negative, but also when you make mistakes and you split them in these two different mistakes, the false negatives and the false positives. So the false negatives, also called type 1 error, are the situations in which you predict something to be not what you are interested in this case not a metal, it was actually a metal. So let's say that you are really craving to find new metal material, and now some of this escaped your attention. So you didn't predict them. So of course there is no way to know this unless you test all the materials that you also make the prediction. That is not probably the best strategy, but let's say that you eventually know this and you would have missed these materials by your model. So this is quite a problem for your model. The other situation probably is less problematic. You have predicted something to be positive, for in this case of being a metal, it was not. Okay, maybe you can live with that, but also you have to factor the fact that you had to check and you found that this material, even if you thought it was positive, so a metal, it actually wasn't. So this is also problematic, but it is interesting to disambiguate these two types of models, because the intervention that you may want to do in order to improve your model might be different depending on which one of the two is higher. So this is to say that instead of just giving the accuracy of the model, so how many times it is correct over all possible outcomes, there are other metrics that people use that are called precision, sensitivity, and specificity, that takes into account how the different errors actually are playing one against the other. Now, I will give a brief overview of unsupervised learning. It is very brief, but I will use a kind of unconventional introduction that tries to unify the general idea of unsupervised learning. So let's suppose that we have data that are organized in a matrix like this. So we have the data points in rows, and each of them is represented by a coordinate that are projection on different features, and this is a certain number of features. And now we want to do a somewhat crazy decomposition of this matrix into two matrices, in which the inner dimension of the product is smaller, and typically much smaller than the number of features here. Why does one want to do that? There would be several reasons, and in all cases is to try and find structure in the data. Let me try to be more precise. First of all, just remember that this matrix product actually means that, for example, the first data point here, the first line, is a linear combination by means of the first line of this decomposition metric multiplied by the rows in this feature matrix. So we are doing this decomposition, x is equal to uv, but actually approximately equal. Of course, this can be equal strictly only if the rank of the matrix X is at most D, and if this sounds pretty new to you, then I suggest that you go back a little bit to refresh your linear algebra, because machine learning is heavily based on linear algebra, so it's hard to get most of what is going on without having a firm grasp on linear algebra. So what you want to do here is then to minimize this, the difference squared between these two matrices, since they are not typically equal. And the way you minimize this difference, so the number of constraints, the kind of constraints that you put, determines which kind of unsupervised learning you are doing. So a situation is when you change the dimension D until your error is somewhat satisfactory with respect to some threshold that you have put beforehand. And this is a situation in which you want to approximate your highly dimensional representation in terms of features by means of a lower dimensional manifold, here a linear manifold in particular, because of the linear decomposition. And you see what is happening. So you have data here in 3 dimension, and you have a 2-dimensional manifold. It somewhat captures the most of what is going on with this data. If you want to neglect the distances perpendicular to the plane, let's say that with respect to a completely unstructured set of data, these have some structure. Disregard now the colors; they are not important for this discussion now. So this is what people call the dimension reduction. The other situation in which you impose that you only highlight one of these lines here, and you find probably a subset of data for which this representation of all the data by only one of these lines here, that is essentially a point in the same high dimensional space. So this situation is called clustering. So you're saying that all these data points are well represented by this point. It is called the centroid of the cluster. So the methodology in this way is recognizing that there are groups of data, and they kind of cluster together in order to populate the feature space, so the high dimensional representation. And this is also another kind of interesting analysis. So in general, this unsupervised learning is trying to find structure in the data, moving from this very basic idea. If there are lower dimensional manifold that on which the data are approximately living on, or if there are subset of the data in which the data tried always to fall. So then Luigi's bylaw will talk diffusively about this methodology. Here is just a few slides that I put together, inspired by actually this talk here, that you encourage you to go and listen to, probably after Luigi's talk. In order to kind of systematize what's going on with the rich zoo of unsupervised learning method. So you see the leitmotif of this introductory lecture is to try to catch what is fundamentally transferred from one machine learning model to the other before you get lost in all the zoo. A very quick word on reinforcement learning. So this is a kind of emerging strategy that kind of deserves to be treated differently from supervised and unsupervised learning. And I'm saying something super quick because it's how to say, quite complex set of algorithms, but there is a basic idea. And I provocatively summarizing this one single sentence, to be one sentence accurate enough. So we are talking about a supervised learning, so reinforcement learning is actually supervised learning, but with the new feature that it starts without a training set. So this is a very not usual situation for supervised learning. So there is no training set, and the algorithm has to build the training set together with learning, the supervised learning model to model the data. And the lingo goes in this way. So there is an agent, so this is an algorithm that changes its state by taking action. So it decides to explore the environment. So let's say you have an algorithm that wants to build atomic structure and starts from one atom, and it has to build atoms around it, and then it starts adding atom first at random, and then it slowly learns how to place atoms in a better place. How does it learn? Because the environment is responding. How does it respond? Well, by giving so-called rewards and punishments. So the game goes in this way, that the agent is exploring the space, so in this example building atomic structures, and then sometimes it calls some kind of feedback from the environment, and in our case would be some ab initio calculation in order to say what was the stability of this cluster, and it could get a reward if the stability was high, so low energy, or a punishment if it was a low stability, so the cluster will actually, say, break apart or something like that. In the meanwhile, the algorithm is learning this potential energy surface, but at the same time, it is guessing what next to look into by balancing the so-called exploration and exploitation of the environment. So exploitation is going towards situations that the algorithm thinks to know well, and exploration is trying to probe situations that the algorithm knows it doesn't know yet, in order to get a more meaningful and more informative reaction from the environment. So that's all I want to say for now on reinforcement learning. Angelo Ziletti will touch upon this in the deep learning lecture, because the way this deep learning reinforcement learning algorithm they are implemented is actually by means of the deep neural networks. Okay, before I close the lecture, I have one word on interpretability, and I really use what in the book of Tip Shirani and co-authors is used to not really define but hint at interpretability. And I put this here at the end as a kind of discussion point because let's say I have the feeling that most of sometimes interpretability is a bit well, maybe not overrated, but there is some overreaction when the word interpretability is heard in the community, especially in the physics community. So you will have half of a lecture dedicated to interpretability given by Gilles Freken towards the end of this course. This will be the perspective of the material scientist, and it will go deep into this, the computer scientist, of course. Here I want to give the somewhat as simple as possible idea from a statistician like Tip Shirani and the other co-authors. So let me go through here. It is often the case that some of or many of the features used in a multiple regression model are in fact not associated with the target. Including such relevant features leads to unnecessary complexity in the resulting model. By removing this feature, that is by setting the corresponding coefficient estimates to 0, we can obtain a model that is more easily interpreted. So interpretability of a model is directly related to its complexity. So if there are only few of the features that are switched on in order to be part of the model, then the model is more interpretable, because we kind of can look into what is happening. And in the book they went further. This is a little bit modified version of what you find in the book there. You have a kind of ranking of interpretability versus flexibility, complexity of the algorithms. And you see that the method that try to have as few features as possible, I will actually talk very diffusely about this method in the next lecture, are high in interpretability, and then the more you make them complex, you will see actually all of these algorithms in the following lectures. So the more they become complex, they become less interpretable. I think not everybody agrees with this kind of vision of what is interpretability, but I thought it was good to conclude the introduction lecture on artificial intelligence machine learning with this thought-provoking diagram. So I thank you for your attention, and I'm ready to take questions.